I forgot to unmute my mic. My apologies. It is still 7 p.m. though. Welcome to the Pinal Geology and Mineral Museum and Pinal Geology and Mineral Society meeting and presentation for January 19th, 2022. Our next scheduled video and meeting and live event will be on February 16th, third Wednesday of February. Speaker to be announced. Tonight, we've got Dr. Raymond Grant speaking on Precambrian rocks of Arizona, or geology of Arizona. I want to just take a moment, remind everybody that we are now in 2022 open from Wednesday through Saturday, 10 a.m. to 3 p.m. We have someone working all those days. We could use, however, some volunteers. If you'd like to get a chance to come into the museum, wander around and help people look at all the rocks and do other stuff like that, please contact us. I'll put up the email address in a few moments. And until then, contact Ray directly, or, if you're local and you know how to contact us, or give us a call at the museum and we'll do that. Okay, I'm going to bring up Ray and say hello to him. There he is.
Does it work?
It works.
Huh?
Can you see and hear you?
Good. I'm always worried. I'll be invisible and silent.
Oh, well, I had you silent for a little while there. Sorry.
That's great. No problem. As far as the museum being open, it's really good. We have had a little problem. Last week, I had to open it a couple days. The gal Christine that's opening it for us was not feeling well. I think I can't tell you about tomorrow, but Friday and Saturday, I'm hoping we'll have somebody there. But after this week, we should be okay again. So.
Well, we could still use some volunteers to help her out.
Oh, always happy to have volunteers. I have a good painting project. Somebody wants to come in.
We have lots of projects going around.
Always.
Okay. Always. Let's see. Dr. Raymond Grant, our director and the primary author of Mineralogy of Arizona or Minerals of Arizona? Mineralogy of Arizona, coming out very, very soon. You can order it through the University of Arizona Publications Department.
University of Arizona Press. Yep.
And looks to be a good book. He was not lead author, but he was involved in the previous edition. This is the new edition. It's updated, and it's got all sorts of good stuff for Pinal County and the rest of Arizona, of course. We can't be too greedy and get the whole 900 pages on us. Maybe some other time. All right. Did you, Kentronics, I passed the question on to Dr. Grant.
No, talking about Epidote, I have a slide with the Epidote in. I'll talk about it then.
Okay. That works.
That slide happens to be in the program.
Okay, so you're going to hear that. Good. He anticipated you. All right, I'm going to try my darndest to get you on the screen with your slide. The
slides are more important than me by a long shot.
Well, instead of me on the screen with your slides?
Whatever.
All right, let's see what we can do here. No, that does that. That does that. And then I'm going to disappear, and I will boop in if there are questions to relay, or I feel I really got to say something. Okay?
Yep.
All right.
I'll say next, and you'll change the slide for me.
I'll say it. Yes, no problems.
Perfect.
I'll get you started in just a moment. I'm going to turn off my camera and then go to do the slides.
Sounds good. Anyway, tonight I'm going to talk about Precambrian rocks in Arizona. Now, there are many, many geologists that know much, much more about Precambrian in Arizona than I do. what I'm doing is giving you just sort of an overview. This would be like a geology of Arizona introductory course to the Precambrian, so that you get a feeling about where they are and what they are. And then if you're serious, you can go on and do some research and find out a lot more. The source of information really is the Arizona Geological Survey. I recommend their website constantly to people. Maps, publications, all kinds of things. So, things I'll miss tonight, you'll be able to go find, I think, at their website. So we'll go on next. So the time I'm talking about for Arizona, you see the word Precambrian way over there at the bottom on the left. And uh, it's sort of not even an official geologic time anymore, but it's a time that almost everybody in Arizona seems to use. I use it all the time. Um, it has, special names, Archean, Proterozoic, etc. And all of the rocks in Arizona are in the Precambrian rocks are in the Proterozoic, which goes from, you can see there on the right-hand side, 2,500 to 542 million years. So that's the time period we're talking about. There, Arizona, we'll see in a minute, didn't exist before, that time period. And then there's all the younger stuff, which is, some other program that we're not having. And up at the top there, I've sort of written that out. We're talking about older Precambrian, 1,800 to 1,400 million years. MA is the geological way of writing millions of years ago. And then the second series of things we call the younger Precambrian, and they're really quite different. You'll see as we go through this, maybe 13,000 to 542 million years. And these are all in the official geologic age, Proterozoic. And then for the Pinel geology people, and since this is a Pinel geology society or geology and mineral society, four different kinds of rocks we see around Pinel County generally. The schist, 1,700, got an extra zero in there. And then a couple of periods of granite and then some diabase. Okay, we'll move on. So if we go back 2 billion years, there was no Arizona. There was ocean here. The North American continent was much smaller, and it existed essentially to the area that's today to the north of us. And this was just ocean. So next. And then over the next, several thousand million years, the plate tectonic activity, you can see the subduction zone there on the left. The red bar there stands for supposedly rocks in the Grand Canyon, and we'll see a little bit about that in a minute. This crust was added, so the older crust, greater than 2,500,000 million year old crust, is on the right, the Archean, and then all of this new, and there's a special word, Proterozoic crust was added, starting about 1.8 and then moving on, till the end of the Precambrian time. So geologists have all kinds of ideas because these rocks are very old. These rocks are quite deformed. These rocks are just scattered. There's just remnants here and there. And so there are quite a few different ideas and interpretations of exactly, where the subduction zone was, where the volcanoes were, where the sediments were. But generally, relatively general kind of agreement that we had to have all of this various kinds of plate tectonic activity that's in the picture there. And just main question is exactly when did it happen and exactly where did each of the things happen? And those things I think geologists will still work on in the future. Next. So this is a map that pretty common that people use showing how North America grew. So the Wyoming area up there at the top, that's the older, and you can see on the right the ages. And then you can see that Arizona was added to over time. And so we have the Yavapai time, And some people think that a little bit of Mojave rocks in Arizona, and I'm not sure. There are some rocks that are probably older or were caught up perhaps in the Yavapai rocks. And then Mazatzel, which would be the area around Pinell County mainly, and then what is referred to as Piccaries. And the Arizona Geological Society just had a program a week, 2 weeks ago. Um, and the speaker there, doing a lot of research, he decided that the Mazatzel and the Piccaries were essentially formed at the same time. So obviously, geologists are still working all of that and all of this timing. But uh, the point is that if we go back to 2 billion years, 2,000 million years ago, there was no Arizona, it was ocean. And since then, these parts of continent, because of plate tectonic activity, have been added on, and Arizona and North America both have grown larger over time. So that's essentially what we're talking about. We're talking about the beginning, the basement, the foundation of the state of Arizona. Next. Uh, I don't expect you to read this. I just want you to see the older Precambrian rocks from the Arizona geologic map. Um, and remember, I'm going to talk about older Precambrian and younger Precambrian. And the point is, you can go to the Arizona Geological Survey. This is a geologic map of Arizona, year 2000. These are the different units that are on the map. Look at the area you're interested in, and pick out the particular unit. Each unit has a color. Each unit has a set of symbols. You can see the one at the bottom is early Proterozoic, and then variety of different kinds of early Proterozoic things all the way up and then to the middle Proterozoic, towards the top. But that's what I would recommend as a starting point if you're serious about looking out, where do I go to see these Precambrian rocks? You can look on that map. You can see the colors, you can see the description from the legend, this legend here from the map. And then it gives you an idea of places you might want to go and look, and to give you an idea about the ages of these rocks. And we'll see as we go through, that they're quite scattered around the southern part of the state. Okay, next. So this is just a rough map showing the distribution of the older Precambrian rocks in the state. And you notice that from the Mogollon Rim north, there's only one place we can see these Precambrian rocks, and that's in the inner gorge, the bottom of the Grand Canyon. So there's that tiny little strip there above the word Coconino. So that's the only place. The rest of that, all the Precambrian rocks are covered on the Colorado Plateau by younger sediments. So we don't see them. We don't see those rocks. You could drill holes and find them because they are the basement that's underneath. And then as we get down into southern Arizona, south of the Mogollon Rim, you can see in an area that a lot of people, geologists, call the transition zone, there's quite a bit of volcanic activity, or Precambrian rocks, excuse me. And then as you get further south, of course, we have all the basins, and the basins, if there's any Precambrian rock, it's all buried again. It's under all the various sediments. So that's why the Precambrian geology has been sort of hard to work on, because it's all these scattered bits and pieces you can see on this map over the state. So you find a bit here and a bit there, and then there's a gap of 10 or 50 or 100 miles to the next bit. And, you've got to try to figure out, well, what in the world happened in between there? What kind of rocks are there? And so that's what, geologists have worked hard, and we have some really good stories, but about how the whole thing, pretty much came to be. But you can see that, it's something that takes a lot of work and thought, and not completely settled yet, I'm sure. That's my feeling. Next. So after we had all of these rocks forming in the plate tectonics that I showed you, we had trenches, we had sediments, we had volcanic activity. Well, these sedimentary and volcanic rocks had to change to what we see today. Today, what we see is metamorphic rocks. So the way to change all of these early Precambrian rocks that formed from the plate tectonic activity is to bury them. So we start having mountain building activity, and those Precambrian sediments and volcanics get buried. And so I just put this in, as try to use my imagination and get you to think about it. Well, maybe this is what it looked like if you would have looked around in Florence, 1,600 million years ago. It might have been pretty spectacular mountain ranges because we really have to bury some of these rocks quite deep, as you'll see in a second here. Next. So the Precambrian rocks that we see, the older ones, are metamorphic rocks. Okay, so that means they've been subjected to some kind of temperature and pressure to change them. And I just real quickly throw this in again. You can do a little research if you want. Phyllite, schist, gneiss. Those are probably the most common of the things that we see. Quartzites, marbles, things like that. But these are the ones that people use to get an idea about the temperature and the pressure. So you can see if we go to some place that we'll see in a few slides with phyllite up there towards the top, well, it might be down 10 kilometers, 6 miles. And if we go to schist, it might be down, buried down. We might need to get it down 15 kilometers, so 9 miles, something like that. Or the gneiss, maybe we have to get down even more, maybe 10 or 12 miles. So the point is, somehow we have to bury those rocks to get the temperature and pressure we need to change them. Okay, they were originally shales, they were originally volcanic rocks, to change them to these metamorphic rocks, which are the ones we see today. And of course, then we have to erode. If that rock is sitting out there, in North Mountain Park or in the Fiesta Peak, then we have to erode that, 6, 9, 12 miles off sometime. Well, we have a long time because these rocks were, formed way back, 1.5 billion years ago. And so, we have a lot of time to erode the rocks off the top so we can actually see them today. Okay, next. So we'll start in the north and look real quick at the Grand Canyon. This is just the stratigraphy thing I happen to have. We only care about that little tiny bit way over on the left side. You see the Yavapai, Vishnu schist, and then the Unkar group. So the Vishnu schist is the old Precambrian, excuse me, and the Unkar group is the young Precambrian. And then everything, and that's only going to be in the inner gorge. And then everything else you see, of course, is all the younger stuff on top. I need to get a quick drink of water here. I've lost my teaching voice since I don't teach. So I, end up with trying to talk too much to some of these programs. Okay, next. So the oldest rock that we have age dates for in Arizona is called the Ells Chasm Gneiss, Ells Canyon Gneiss, or Ells Chasm. It's a locality. It's on the Colorado River. If you go on a boat trip, you stop there and walk up. It's very scenic. It has some waterfalls. There's a picture of what the rock looks like in the canyon. That's the Colorado River at the bottom. If you go on the Trail of Time along the south rim of the Grand Canyon, which is pretty neat because they have the whole history of the Grand Canyon out there. They have a sample. So I have a picture that I took there of that sample of the Ells Chasm Gneiss. And it's dated at, 1.84 billion years or 1,840 million years old. And that's the oldest rock that we have so far in the state. And there may be some older things, some of the Mojave stuff that's caught up here and there, but I haven't seen any older dates yet. Next. The Vishnu schist is the most common rock we see in the inner gorge in the Grand Canyon, 1.8 billion years or so. GA is what we use for billion years. And the important thing here is you notice how it stands up vertical. So if you're driving around Arizona, road cuts like driving to Flagstaff or anywhere you might stop, if you see things that are going straight up and down like this, and you'll see some more pictures as we go through, then you're probably looking at the Precambrian because remember they were all buried down there deep, and they've all been pushed up. And when they get pushed up, they tend to end up, with this sort of vertical appearance to them. So this is the Vishnu schist in the Grand Canyon. Next picture shows you can see it at the bottom of the canyon there. The horizontal hard layer, the Tapete sandstone, is just 510 or so, maybe million years. So we're looking at something that the early geologists, I think Gilbert and then Powell, used the term the great unconformity, because between the schist and that horizontal layer of sandstone, well, we're missing, 1.5 billion years almost of geologic time. So we have no history there of what was happening. Well, what was happening? Well, the mountains were all pushed up and they were eroding away. In some places, we'll see the younger Precambrian, which would be stuck in between those two ages. But a lot of places around, including here, in this area, we see the old Precambrian, and then the younger rocks are just stuck on top of them. Okay, next. This is the same unconformity on Route 87 north of Payson, if you something a little easier to get to than down in the bottom of the Grand Canyon. Just a few miles north, there's a granite. The granite is like a 1.6 billion year old granite. And then there's the Tapete sandstone, the 500 plus million year sandstone on top. It's called a nonconformity when you have two different rock types like that. And I put this sphere in Wolfgang Mueller in Tucson. And you guy has to be interested in geology. He carefully sampled across that unconformity, and he cut, I think, 2 spheres, and I was able to get one of them, and he has the other one yet, I think. There may be others, but I think that he told me when I got this that there were only 2 of them. So the 1.5 billion year time gap is in that sphere, and of course it's in that outcrop in the rock there too. But I had to show you that sphere. I really think it's quite an amazing piece of rock to hold in your hand. Okay, next. Not critical to see all this, but the idea is that there are a lot of ore deposits in the older Precambrian. And again, you can go and look these things up. It's been published. You can see they're mostly, again, in that transition zone. They're right when you get to the edge of the Colorado Plateau. And that's where most of the Precambrian rocks were on that map, showing the location of them. So that's where they're located, and that's where the ore deposits, you would expect to find them. And if you can read the legend there, there's all kinds of gold and all kinds of sulfides and copper and metal deposits and things like that. And I just wanted to show you one kind, because it's really kind of quite interesting, kind of a deposit that we have in Arizona. It's an ocean floor sulfide deposit, and you can see there in the legend that they're very often called volcanogenic massive sulfide deposits. And these formed here, they started forming, 1.7 billion years ago or so in the state of Arizona. So the next picture, just a little bit of geology on how these form. Next. So at seafloor spreading today, modern times, we know the ocean's spreading apart. There's a mid-ocean ridge. New magma comes up and pushes apart. The Atlantic Ocean's getting bigger. The Pacific Ocean is shrinking a few centimeters a year or so, depending on the rate of, continental drift or plate tectonics. Next. The new ocean crust that comes up is from the mantle. The mantle is melting, and it's constantly moving up, and that's magma moving up is pushing the ocean apart, and we have this ridge, mid-ocean ridge, and so you can see that's what's happening in the Atlantic Ocean today. Okay, next. And in basalt, there's a little bit of metal. It has 100 parts per million. 0.001% copper. It has a little bit of molybdenum, a little bit of lead, a little bit of gold and silver. The gold amounts to, 0.0008%. So all basalt. If you just go out and pick up a chunk of basalt, it'll have these trace amounts of these various elements in them. But there are geological processes in it we'll look at here that enrich these metals and actually form the minerals, that we can mine, that are actually mined in these ore deposits. Okay, next. So I'm going to talk about the black smokers in a second, but just first to sort of see how they got here in Arizona. So if we go back to this Precambrian time, remember I told you there was subduction and new continental rocks were forming, and so these ore deposits are forming on the ocean floor. And then there's two things that can happen to the ocean floor. It can get subducted down, and that's probably the story about some of the more recent copper deposits like Ray and Bisbee and those things. And that's a different story than we're telling tonight. And some of the ocean floor can get pushed up and become involved or part of the continental rocks, part of the new landscape. And that's what we see back in these Precambrian ore deposits. Okay, next. So the black smokers are where we have the basalt. Molten basalt is coming up at the mid-ocean ridge. Seawater is soaking down, into meeting up with that basalt. And it turns out that salt water preferentially leaches out copper and gold and lead and molybdenum and zinc and sulfur. And the material that gets leached out by the seawater, as it gets hotter and hotter, it starts coming up through, along the ridges as these black smokers. And what the black smokers are, they're really sulfides. And we'll see in the next picture that they're the metal. And you can see how hot they are on there. They're, extremely hot, and they hit the cold seawater. And of course, immediately you get this black precipitate that starts to form there, starts to crystallize. And then I think if you just push the button again, it'll change that picture. I don't know if it'll work on here or not. Didn't. Okay, anyway. So at this vent, what we see is pyrite, iron sulfide, chalcopyrite, copper iron sulfide, salarite, zinc sulfide, galena lead sulfide. And the copper can be enriched actually by thousands of times. In fact, I don't know if you look in the news all the time, they're talking about potentially mining on the sea floor. And one of the things they could mine on sea floor are all these various metals at the black smokers. And if you look very carefully at this picture at the bottom left, you see the black crust and then sort of the white core, the white rock in the middle. So that's one of the black smokers that they've collected on the ocean floor, and brought back from the deep sea dives. Okay, and the next. The biggest of all of these old Precambrian massive sulfide deposits is in Jerome. So this was a picture when I first came here almost 50 years ago. And if you could read the sign, I don't know if you can see it, it shows that the population is dropping, and it says Ghost City at the bottom. And if I was smart, I would have bought property, of course, back 50 years ago in Jerome, but whatever. Next. United Verde mine is the mine that was mining this massive sulfide deposit, extremely rich. The next picture shows the smoker. So you see that's a specimen that collected at the United Verde mine, and it's that black rim. I mean, it's almost unchanged. People found these things, and that led them to say, well, yeah, these are exactly like the black smoker specimens that geologists, deep sea people have been collecting on the ocean floor. And so, putting it all together, they were able to figure out that that's how these deposits formed. Okay, next. If you want to learn more about that, the nice exhibit at the Jerome State Historic Park Museum, it's in the Douglas Mansion there in Jerome. Next, they have a story about the, seafloor deposition of these massive sulfide deposits, and how they, were formed. They have stuff about the mine. I think the next one's a little bit of the story of, how much copper. I mean, we're talking about, millions of pounds of copper, an extensive amount. They were extremely rich deposits, extremely valuable. They were some of the early ones mined here, obviously. Jerome's one of the older towns. And, real interesting, for the age, the deposit, the time that they were formed back in the Precambrian. Okay, next. And I always put this in when I talk about Jerome because to me it's amazing. On your way to the museum, to the historical park, state park, you pass this head frame and there's a place to park, and there's a sign that says the Audrey Head Frame Park in Jerome, and it's the United Verde extension mine. It was an underground mine. Part of the deposit was downfaulted. So there was a part there in the open pit, and they had underground mining there too. But the part in the open pit was a United Verde mine, and then they had this United Verde extension, which was on the other side of the fault. And when you walk out in the bottom left part, there's actually a glass floor. In the next slide shows you what you see. It's this incredible deep shaft that he just disappears into oblivion. To me, it's just amazing to see something like that these guys dug these shafts, they're so deep. It's just incredible. Okay, next. So that takes care of our massive sulfide deposits. Another thing that happened in this older Precambrian rock is that we get the deposition of granite and pegmatites. And there's a number of different ages of granite. And the one thing I have to say about granite, if you just pick up a piece of granite, or if you brought me a piece of granite, or most of y'all, very difficult to tell the age of the granite by just looking at it. So we have 1.65 million year old granites, we have 1.4 billion year old granites, and we have many, many younger granites too. So, difficult to tell the age. Here you can see in the Grand Canyon in the inner gorge again, the schist is on the left and the granite is all pushed up, intruded into it. So it's obviously younger than the schist because it's intruded into it, but you can see it's older than the sandstone up above because it's been eroded off and the sandstone's been deposited over it. So by doing all these observations, geologists can, look at all the relationships and get themselves a pretty good idea of the age. And of course, nowadays they can do absolute radioactive age dating and figure out the age of the granite. So anyway, the point is that in the older Precambrian, there was a lot of granite. And then we had the pegmatites, which are special sort of a granite, big coarse grain granite, a late thing that happened with you have to go study pegmatites if you want to, learn a little bit more about them. And the next picture, if you get Dick Johns has a early state publication about pegmatites in Arizona, and he has the Arizona pegmatite belt. You can see there across the state. They're actually pegmatites scattered over other places, but that's the main belt. You can see one of the pegmatites there on the left. Cutting across the metamorphic rocks. You can see the somewhat vertical foliation or attitude of those rocks, and you can see that the pegmatites are coarse grain. They have big crystals. Next picture. Well, on the left is the Kingman Feldspar mine, and if you go read about that, some of the crystals there apparently were, the size of a car garage. I mean, they were gigantic feldspar crystals that they mined, and they mined them for, glass, ceramic industry. And fairly extensive and interesting. You see that black stripe across there. That's a diabase intrusion, and we're going to talk about that later. It's a younger Precambrian event. So, the pegmatite was there and that cut across later. But the thing at the Kingman Feldspar mine is a lot of really unusual minerals, and the rare earth minerals and uranium minerals, and they're allanite. And that particular place was the first neodymium allanite in the United States was found at the Kingman Feldspar mine in just north of Kingman. So some interesting minerals, the stuff in Maricopa and Yavapai County, the variety of rare minerals. And again, in the mineralogy book, we have quite a bit about all these pegmatite minerals because they're, quite a large number and some quite rare minerals that are found in the pegmatites. Okay, next. So I wanted to say a little bit. Hopefully, we have some people from Phoenix listening, and if you go to the parks, Phoenix has a fantastic park system: North Mountain Park, Piestewa Peak, South Mountain. All of these parks have Precambrian rocks in them, so it's a good place to go see them. The parks are there. You can hike around. You can look at all the different rocks. If we go to North Mountain, Piestewa Peak, we can see that these things were buried quite deep because their degree of metamorphism that we see. And like I said earlier, then we bury them down, 9 miles, 12 miles, and then we have to push them back up and erode all that material off. But of course, since these are all, old Precambrian, we have lots of time to erode them off to get them to where we see them today, right on the surface. This is Arizona Geological Survey map. You can find it on their website. It's a geologic map of the Phoenix Mountains. It's quite detailed, and it's one of their most popular publications. It gets on their popular publication list very often. So you can look at each of the mountains. You can look at the legend. It's quite detailed. Probably hard to see looking at it there, but go on the website and you can look at it pretty carefully, and you can find out for any given place where you're hiking or visiting in the Phoenix Mountains. It's from North Mountain there or down through Cross Camelback, you can get an idea of what the age of the different Precambrian rocks are that you can see. Next. So, and then I just put the cross section. There's the title of it, The Geologic Map of the Phoenix Mountains, Central Arizona, Julia Johnson and Steve Reynolds, etc. That's the publication. And you see the date. And North Mountain, these two pictures are from North Mountain. The rock there is pretty much a phyllite, so it's a relatively low grade metamorphic rock. What that means is that the crystals, it stands up vertically, but the crystals are generally quite small. You don't see big crystals there. Okay, next. Piestewa Peak, a little bit more metamorphism there. Good hike. The top, because the top is a harder rock, it turns out the top is quartzite, but we see a bunch of the schist, different kinds of schist, on the slopes. And again, I don't know if you can see in the picture, but they tend to be, pointing up vertically. Okay, next. Quartzite, it's just sandstone that gets heated and sort of not to the melting point, but so that it all fuses together. So you don't have a sandy texture anymore. You have this sort of smooth, hard texture, but it's essentially almost 100% quartz. Next. There's some volcanic rocks that have been metamorphosed. Rhyolite, again, you can see some of the phenocrysts or crystals, larger crystals that were in that. So there were volcanic rocks, there were sedimentary rocks, but they've all been metamorphosed. But these are all rocks that occurred as part of this plate tectonic activity back in the old Precambrian. Okay, next. Kyanite's an aluminum silicate, fairly high pressure mineral. There actually was a small kyanite mine. You don't really see it. It's just off the trail that goes up to the top. And the guy supposedly, kyanite was used for, I don't know, spark plugs or something, some sort of high temperature thing. And supposedly he mined a few tons and carried them out on burros and sold it somewhere. But the point is that the mineral kyanite is there. Next. There's also Piemontite. If you look around, unfortunately, it's a city park and rock collecting is supposedly forbidden. So you can look, but you're not supposed to take things home with you. Piemontite is a manganese. That's why it has the red color from manganese epidote mineral. And it's found there. You pick up some of the schist on the slope at the bottom of Piestewa Peak, you'll see the red needles in the schist. This is just a Google or satellite view of South Mountain. If you look right in the center, there's sort of a white band across South Mountain. Yeah, and everything on the right side of the mountain is granite, and everything on the left side is the Precambrian rock. Now, when I first came here, if you go back and look at the old state maps, that granite is listed as a much older granite. And I was going to go look up and see exactly what age they put it, whether they put it, at 70 million years or whether they put it at, 1.4 billion years or what they did. But since I've been here, they've done a lot of work, and it turns out that granite's quite young. And that's what I was saying about the age of granite. That granite's only like 23, 26 million years old. And the rock then on the other side, on the west side of South Mountain, is the Precambrian rock that you can see. So, you can go to the next slide, just a picture of South Mountain. That white line or that gap is right through the middle there. So everything on the left of your picture is the young granite. Everything on the right of your picture is the Precambrian rock. And when you get there, it's really quite different than any of the other Precambrian rock that I'm going to show you tonight. It's an amphibolite or an amphibole gneiss. So it was probably volcanic, like basalt or something similar that formed. And again, if you remember back to when I talked about the depth, it was probably a higher temperature metamorphism, so maybe buried a little bit deeper than some of the other rocks like the phyllite. So what I'm saying is that South Mountain was deeper and got pushed up than North Mountain, which wasn't quite as deep. So different parts were pushed up at different rates, and of course, then the top material all eroded off. Okay, next. And this is just a place that up there on South Mountain, I think it was a little dance thing or something, or some kind of a place where they did some kind of activities. And it's a phyllite. It's a really nice phyllite, and it was mined apparently. I've never actually found the site, somewhere in the north side of Phoenix, and they carried it over there and used it as a flagstone. So I just put it in there. So if you're up in South Mountain and you go wandering around and you see this phyllite, you'll know. There were gold mines there too in the Precambrian rocks. Okay, next. And then just a little bit about Pinell County again, since we're the Pinell Geology and Mineral Museum. And I guess the YouTube talk about geology of Pinell County is probably still up there. If you want to, see a little bit more about the geology of Pinell County, you can go. I'm just going to briefly touch on it today. So we had the sediments and the volcanic rocks associated with the trenches and island arcs, and just a little bit younger than the rocks. Remember, as you go north, you had, the Vishnu schists, the Yavapai schists, they're older. And as you move south in Arizona, the plate tectonic activity, stuff is piled onto North America, starting in the north and keep moving south as Arizona got bigger and bigger. So the point is that then these rocks were buried and they changed to phyllite and schist. Okay, next. So the Pinell schist is the oldest rock we have. I didn't say anything, but the geologists name rocks, they name them after a place. So, if it's a Vishnu schist, it's named after a place in the Grand Canyon, or the Yavapai schist, Yavapai County, or a place in, there. Pinell schist was named after the Pinell Mountains. And it's the oldest rock we have. And probably don't need to say much more about it. There's some granite. We'll talk about that. Not a great map, but again, the point here is that these rocks are so scattered. When we get to the southern part of the further south you go, the less and less we see of these rocks. In Phoenix area, in the Phoenix Mountains, there was a lot of Precambrian rock. As we get down into Pinell County, you can see there's a good batch of it right around the north end of the county, and then little bits scattered here and there. And you can go all the way to Bisbee, and there's even a little bit of Precambrian rocks in Bisbee. I mean, they're everywhere under the state. They're just covered, in most places. It's the basement rock, essentially the rock that's underneath, every other thing, but they're all buried under all this younger material. Okay, next. The picture of Pinnell schist, just locally here, not very far from where I live. Quartz and mica. The best place, probably the easiest place to see it. The green area is a map that I'm going to put in the museum showing the different formations in Pinal County. And so the green area is where the Pinnell schist is found, the Route 60 in Superior, you see there. So as you go over Gonzales Pass, you can stop anywhere along there. That's all Pinnell schist that's present along Route 60 there. That's probably the easiest place that I know of around Pinal County where you can see lots of Pinnell schist. Then we have a granite. There are two granites that we find from the Precambrian, the 1.65 thousand million year old granite, which obviously intruded into the schist. Next. One of the places, this is behind the Walmart on the Hunt Highway and Gary Road. Just behind there's some hills. They are all this old granite. I think there's a picture, the next picture, I think it's in there. Yeah, so all that green stuff is called epidote. So we already had our first question of the evening is, in the older granite, because I don't see this epidote in the younger granites. And so the question is, when did the epidote form? And I think that's a great question, but I'm not really sure I can answer it. Epidote, forms as a low-grade alteration, of these rocks. I don't see epidote in any of the other granites, so that might be a clue that it formed, relatively early before the other granites formed, or it could even be a relatively recent kind of feature associated with the, uplift of the granite to the surface associated with weathering. So I sorry, kept you waiting, but I have no real clue about the age of that epidote. But the story is right that the older granites seem to have the epidote, and there's epidote in other kinds of rocks, contact metamorphic rocks and things, but the younger granites, I have not seen the epidote. Okay, next. Then there's this younger granite, which is more widespread and much more common around Pinal County and around southern Arizona, actually. Part of this Picaris, Mosatzal orogeny kind of activity. So next, I just put one picture in the Walker Butte Granite Quarry. That's just off of the Hunt Highway. And again, so that's 1.4 billion years or 1,400 million years. And there's, lots of younger granite too, but these are the Precambrian granites. Next. And then I just put the symbols from the state map for the younger Precambrian. So again, I would go to the state map and look at it. If you look on the right, you see the older Precambrian, Pinnell schist and then granite. Then we come to, the end of that time period. And then you see things like the Pioneer Formation, Dripping Springs Quartzite, Mescal Limestone. These are the younger Precambrian rocks, and they're relatively undeformed. They're relatively still sedimentary layers. That's what they look like. They've been heated and squeezed maybe a bit, but they're still relatively, recognizable as the sedimentary layers. They're not schists and gneisses and those kinds of things. And they apparently started being deposited about 1,300 million years ago. As sand and conglomerate and clay and mud and limestone. And so we had, this period where there had to be some ocean and there had to be rivers and there had to be things like that flowing across the older Precambrian rocks. Okay, so again, go to the state map. You'll see those two symbols. The next is a map of where we see them in Arizona. Again, if you look way up in the Grand Canyon, there's a little bit up there, nowhere else on the plateau because they're covered completely by all of the younger rocks. And then this big mass, and that's around Salt River Canyon. So the best place to see these rocks, and I'll show some pictures, is probably in Salt River Canyon. But you can see they get down into Pinal County a little bit, and a few scattered, just little tiny scattered bits around. But the big mass is, you can see the black area there in the center of the state, sort of. So that's the place where you see them. Next. So Salt River Canyon, you can see they're still horizontal. They haven't been, tilted there much. They haven't been affected very much. I mean, we're talking about rocks that are 1 billion years old, and they still look like, the much younger rocks we see. The very top of the picture there, those are the younger rocks from the Precambrian, but everything, under that sort of hump is all the older, younger Precambrian. Next. In the Grand Canyon, they've been tilted or faulted a little bit. So you see where the word younger Precambrian is actually written, that's that horizontal sandstone, the Cambrian, the 500 million year old stuff. And then underneath you see these tilted layers. But again, they're covered over, of course, you can see by that thick sequence of younger rocks. So we don't only see them in the deeper parts of the canyon where the canyon's just been eroded down deep enough. Of course, in southern Arizona we can see them. In Pinal County, I think the next picture. Yeah, this is just north of Superior. You see the map, the blue colored rocks on there are these where you see these rocks, the younger rocks. And so there's this hill just north. If you take Silver King Road, you pass along the base of this hill. Further down towards Kelvin, down in that area, again, there's a bunch. You can see them there at the very bottom of that map, the blue area. So we do have some good outcrops of younger Precambrian stuff in Pinal County. Not a lot, because there's not a lot here, but mainly the Salt River Canyon's a place to go. Next. Just what some of these rocks are. The Barnes conglomerate, good conglomerate, pretty well cemented, silicified. So, it makes a good hard rock. It's a good rock to find in the stream channels. I know some people like to cut it for bookends and making things out of it because it's a pretty good solid rock. Next. Quartzites, just like the older quartzites, we have some younger quartzites. Next. As you wander around in the Gila River and the Salt River, almost all the cobbles are quartzite because it's a hard, most resistant rock to weathering. There'll be some granites and some other things, but you don't find basalt cobbles and you don't find diabase that we're going to talk about next, but you find all kinds of quartzite, and the quartzite comes in red and green and white and gray and all kinds of variety of colors depending on what the sandstone or color was when it was squeezed and changed into quartzite. Okay, next. And sort of the final thing in the young Precambrian is the area was sort of pulled apart, and there's a name of this whole event. And diabase, which is similar to basalt, but it cools slower, so it's a little coarser grain, intruded along the cracks, and then it pushed in between the layers to form sills. And so it's sort of the youngest of these Precambrian rocks that we see. And because it's like basalt, it tends to usually weather a little faster than the surrounding rocks, but we'll look at some pictures of it. Again, the best place to see this age rock, those big black sort of areas or stripes, these are the diabase sills. They've intruded, the magma's pushed in between the layers of sedimentary rock. And so they were horizontal when they were deposited, and the magma cooled there underground. So that's why it cooled. That's why it's a little different, a little coarser grained. And diabase, I think, is strictly an American geologist term. I think other people use different terms. Okay, next. One of the things that happened is when the diabase came in contact with the limestone, the Mescal limestone in particular, and that's that white rock there, it deposited serpentine and asbestos. And so in the Salt River Canyon, there's some really in the past, active asbestos mining. Of course, asbestos has a bad rap now, but some of the fiber there got to be, 3, 4, 5, 6 inches long, maybe even longer in rare cases. So this long fiber was really great for, processing and using to weave cloth or weave, um, fireproof kinds of things out of. So you can go to these mines and you can find the asbestos and you can find the serpentine that formed there. But it's part of the younger Precambrian. It's a kind of a special ore deposit in the Salt River Canyon area mainly, where the diabase intruded into the carbonate-rich rocks and deposited this, and actually particularly into dolomite, which is a magnesium carbonate, and chrysotile, the asbestos, is a magnesium silicate. So, that's the source of that particular element, the magnesium. Okay, next. Again, this is along Gary Road, just north of the Walmart on the Hunt Highway. And again, you can see there's the old granite. It's the 1.65 granite, the granite with the epidote in. And then the younger diabase cut up across it. And you can see that the diabase is weathering a little faster than the granite, because the iron-rich rocks weather faster than the more silica-rich rocks. Next, just to show you might be out walking, and if you come to this black sort of relatively fine-grained rock, keep your eyes open. It could be that diabase again, because the diabase tends to weather away and we tend not to see it. Okay, next. So there we go. We've come full circle. Suddenly it's 500 million years. And what does Arizona look like? Well, it looks like I showed you in the very beginning. The ocean comes back. Those horizontal layers of sandstone and things that were deposited at the edge of the ocean. And then we have some of the other Paleozoic rocks. So Arizona is under the ocean again. And that's the end of my story about the Precambrian. Thank you.
Well, it sounds pretty much like if you want some oceanfront property as Arizona, you just have to wait 500 million years or so.
Yeah, I think it could be back. Yeah, we got to get rid of some mountains, but then we're set.
Yeah, well, 500 million here, 500 million there. Pretty soon you're talking about real time.
Yeah, yeah, these rocks so old. Well, that's what I tell people. You can actually go out and touch a rock that's 1.7 billion years old. That's incredible in a sense, isn't it?
It is.
Yeah, you can go pick it up. It's that old at all these places I showed you.
It's wonderful. All right. If you have a question, please put it in the comments before we go. I'll give you a couple of minutes to that. Thank you, Dr. Grant.
Well, I'm glad to do it. Hopefully we'll get not the inbred speakers from the museum. We'll have some good
Well, next month, February 16th.
Yep. I'm hoping we have our Australian talk, but we'll see. I can't promise.
We're gonna. Oh, we're trying to get.
We do have that field trip. If you're watching, and if you're not on my newsletter, or get a hold of me, email us, and and I'll be happy to send you. We're going to have a field trip just for Chalcedony roses to start, and it'll be the last Sunday in January. So it won't be this Sunday, but the week after. We're trying again to get things started.
Okay, there's our email address down below. For right now, let's see. Kentonix has another question. It does have. Is the diabase on Gary Road part of the same injection event as the ones in the Salt River Canyon?
Well, they all formed around the same time. Yeah, over actually a wide area, all the way over into New Mexico. It might be plus or minus 5 million or 10 million. I'm not sure how, these volcanic activity or igneous intrusions sort of seem to move slowly with time, as you look like at the magma coming up recently it come up in one place, and then, a couple thousand years later, it come up a little further north, maybe, or something like that. So, it's the same formation. It's the same diabase. I can't tell you what the range of time is. I have a feeling that if you looked at all the diabase scattered all over the Southwest, you'd find some tens of millions of years difference in the actual radioactive age of them. But essentially, they're the same rock. Yeah, exactly.
All right. And Brian says, thank you. That's what I guess that's what we got for this month.
Well, our hour's up. We're timed it good.
Yep. We'll be back next month on the third Wednesday, February 16th, 2022, with another speaker. Well, hopefully a different one.
Yep. I guarantee you it'll be different.
Yeah. I'm starting to work on mine.
No matter what. Right. Yeah. All right.
All right. Thank you all for watching. Thank you. Whether you were here live or you're watching this afterwards, thank you all for watching. I really appreciate it. And we'll see you next month. Check out the website for more information. And that website is, of course, penalgeologymuseum.org. And again,
Bob's done a good job on the website, so go see it. There's lots of good information there. Yeah.
Oh, shucks. But go see Chris at the museum 10 to 3 Wednesday through Saturdays.
I'm just not sure about this week, but after that, there won't be a problem. Yeah.
We're hoping. All right. And see, that's just for those watching later. That's only through May. We close for the summer, and then we'll be back in September with new hours.
Okay.
But as far as I know,
I can click leave studio, right?
Yep. Thank you very much. All right. Dr. Grant's gone, and now I am. Thank you very much for watching. This has been the Penalgeology and Mineral Museum and the Penalgeology and Mineral Society presentation for January 2022. Good night.